Good morning, students. Today we are going to discuss about the torque acting on a rigid body and angular momentum. So let us see what is torque. Torque means it is the rotational effect of force. The rotational effect of force. For example, we all have seen doors. When we open the door, what are we doing? The doors are fixed at one point, which is called hinges. There the door is fixed, the handle is kept on the other side of the door, we hold the handle and we pull it. So actually the door is not falling. When we are pulling it, the door is not falling. Instead, the door is rotating. So imagine this is the door, and when I pull, what is happening? Here it is fixed at the hinges, and when I pull, the door is turning, and if I want to close, I will push. So the door is again turning back. So this turning effect of force, see, when I apply the force, it causes a turning effect. When I pull, again it causes a turning effect. This turning effect of force is called torque. Now, it is measured as the product of the magnitude of the force and the perpendicular distance between the line of action of force and the axis of rotation. So the torque is measured as the product of magnitude of the force and the perpendicular distance between the line of action of force and the axis of rotation. Which means, like this, I am applying a force F, and this is my hinge. From here to here you take a distance. Okay, understood? This is my hinge. So from here to here you take the distance. That distance is R. So force into R will give the torque. So I will be writing like this. Torque is equal to, torque is written by a letter like this, which is called tau. Tau, it's a Greek letter. So torque is represented by a letter like this, which is force into perpendicular distance. So I write torque is equal to F into R. What is the SI unit of torque? Force, Newton, R, meter. So SI unit is Newton meter. Okay, SI unit of torque is Newton meter. Yes, this torque is also vector quantity, and since the torque is a vector quantity, we will take the same right hand thumb rule as I discussed in the previous video. We will take the same right hand thumb rule as I discussed in the previous video as the direction. That means if the body is rotating in the x-axis, in the positive axis, or in the anti-clockwise direction, torque is considered as positive. And if the body is rotating in the clockwise direction, torque is considered as negative. So please make a note of that. If a body is in the anti-clockwise direction, torque is positive, and if the body is rotating in the clockwise direction, torque is negative. Now look about the previous example that I told. This is the door. So suppose the door is moving from here to here. So I will take my right hand, look at my right hand, I will take my right hand curve like this, and my thumb is upward. So in this direction, as the door moves from here to here, in this direction, torque is upward. The thumb is pointing upward. Now what happens if I pull this back? So it is turning from here to here. So my right hand will curve like this, the thumb is down. That is negative. That is why I told anti-clockwise torque is positive, clockwise torque is negative. Now, the moment of force. Moment of force means rotational effect of force, which is the torque itself. So, torque is also called moment of force. So, the moment of force vanishes, that means moment of force becomes 0 if the magnitude of the force is 0. Number 1, the magnitude of the force is 0. Number 2, the line of action of force r sin theta passes through the axis is 0. So, if the magnitude of force is 0 or the line of action of force, that is r sin theta, the line of action of force passes through the axis is 0. That means F0 or r sin theta 0. At that time we can say the torque is 0. Now let us see how to get the expression for the force. How we will find the expression for the force. Suppose, look at this figure. In this figure you can see a particle is situated here, and this particle is allowed to move in the circular path, keeping this as the center. This is the center of the circular path. So, the particle P is allowed to move in the circular path where this is the center of the circular path. I am applying a force like this. First, I will draw a position vector. That means a vector drawn from this green dot, vector drawn from here towards the particle P. That means vector drawn from a green dot towards the red dot. That is vector r, the position vector. And I just extended vector r to that side. The force that I have applied makes an angle theta with the position vector. The force that I applied makes an angle theta with the position vector. Okay. Now, I extended this force backwards till here and I draw a perpendicular towards this point. Okay. I extended this dotted line backward and I draw a perpendicular towards this. If this angle is theta, I can mark this angle is also theta. I mark this point as O, A, B. Okay, I make that triangle as OAB. In that triangle, in triangle OAB, what is sin theta? Sin theta is opposite side by hypotenuse. So, I can write OB by OP. Opposite side is OB and this is OP. OB by OP, which is OB by R, because you can see OP is R. Now, this is the perpendicular distance. So, I am writing torque is equal to force into perpendicular distance. This is tau. Tau is equal to F into OB. F into OB. This is the perpendicular distance. Now, torque is equal to F into, what is OB from here? Sin theta is equal to OB by R. So, what is OB? Take R to this side. So, OB is equal to R sin theta. Therefore, instead of OB, I write R sin theta. Therefore, tau is equal to Rf sin theta, or in vector form torque is equal to R cross F. Torque is equal to R cross F. This is the expression for the torque. So, here I wrote tau is equal to F into R sin theta, then I made it tau is equal to R of sin theta, and AB sin theta is A cross B, so vector tau is equal to vector R cross vector F. I am not writing F cross R. Why? Because we studied cross product is anti-commutative. Here first I kept a particle and there is a position vector. First comes position vector, then only I am applying the force. So first vector should come first. That is why I talk tau is equal to vector R cross vector F, or tau is equal to R of sin theta. R of sin theta you can also write FR sin theta, that doesn't matter, but in vector form it should be written as vector R cross vector F. That is the expression for the torque. Now, we can just take down this, and I have to say a little bit more. So tau is equal to R cross F or R of sin theta, and now just read this: torque vanishes when F is 0. Because of this equation, when F 0, torque is equal to 0. When R sin theta is 0, again torque is equal to 0. Now, when is torque maximum? That also you have to note down. When is torque maximum? Theta is 90 degree. That means force and perpendicular distance. Force and distance are perpendicular to each other. At that time, theta is 90 degree and torque is maximum. Okay. Yes. So that's all about torque. Now comes angular momentum. What is meant by angular momentum? Angular momentum means it is the moment of linear momentum, or I will say it is the rotational effect of linear momentum. Okay, rotational effect of linear momentum, or I will say moment of linear momentum. In the previous topic we told torque. What is torque? Moment of force. What is angular momentum? Moment of linear momentum. Okay. So it is the rotational analog of linear momentum. It is also referred as the moment of linear momentum. And the angular momentum can be written as vector L. Vector L can be written as vector R cross vector P. Vector L is equal to vector R cross vector P, where vector P is the linear momentum, vector L is the angular momentum. Now, the rotational analog of Newton's second law of translational motion for a single particle, I can write this as dl by dt with a vector sign is called torque. dl by dt is called torque. So you remember, no, F is equal to dp by dt, Newton's second law. F is equal to dp by dt, that is Newton's second law. Here I am just taking the rotational analog of Newton's second law. So instead of force I am using torque. Instead of P, linear momentum, I am using angular momentum. So instead of F I use torque, instead of P I use L, so tau is equal to dl by dt. This is the rotational analog of Newton's second law of motion. Okay. Now angular momentum is also a vector quantity. Its direction is given by right hand rule. Okay, angular momentum is a vector quantity, direction is given by right hand rule. Please note that also. So now we are going to find the expression for the angular momentum. Expression for angular momentum. So give the heading, derive an expression for angular momentum. Look here. To derive angular momentum, we take the same figure as we took in the case of deriving the torque. Okay, I am using the same figure that I use to derive the torque. So I am going to write the expression here also, here itself. Okay, now just see what is the change in the figure. Here I applied a force, right? When I apply the force, the linear momentum will be in the direction of the applied force. When I apply a force, linear momentum will be in the direction of the applied force. So I mark linear momentum here as P, and that linear momentum makes an angle theta. So as I did in the previous case, I am just putting theta here, and this is O, this is A, this is B. You have to redraw the figure here. Okay, I hope you have written the heading, derive an expression for the angular momentum of a particle, and then draw this figure. This is the particle at the point P, and vector P is the momentum acting on the particle. Now angular momentum is denoted by capital letter L. That is what I have written here. Now you take the same triangle, in triangle OAB, sin theta is equal to OB by OP. OB by OA, and you know OA is R, so OB by R. Then what is OB? OB is equal to R sin theta. Now I want angular momentum. Angular momentum is equal to linear momentum into perpendicular distance. Angular momentum is equal to linear momentum into perpendicular distance. So angular momentum is denoted by L, linear momentum is P, perpendicular distance is OB. And what is OB here? R sin theta. Therefore I can write P into R sin theta. So I will rewrite this as L is equal to R P sin theta, or in vector form, vector L is equal to vector R cross vector P. So this is the expression for the angular momentum. So you are getting the same, I am deriving the same pattern as I derived for the torque. And here also, as I told, first comes position vector, then only linear momentum is applied. Particle is here and position vector is there, and then only the linear momentum is applied. So that is why it is R cross P and not P cross R. So take down the derivation. Draw the figure and take down the derivation. That's all for now. Thank you.